Okay, Assalamu alaikum students. Let's do an example on Carnot engine. In this example, a Carnot engine that operates between high temperatures TH 850 kelvins and the low temperature is TL 300 kelvins and performs 1200 joules of work for each cycle. That takes 0.25 seconds or quarter of a second to complete one cycle. Okay, in this example, the Carnot engine, as you know, it has two reservoirs. It operates between two temperature reservoirs, high temperature reservoir and low temperature reservoir. Here, high temperature reservoir is at 850 kelvins and low temperature reservoir is at 300 kelvins. So when it absorbs some heat energy from the high temperature reservoir, it performs 1200 joules of work during one cycle, and the cycle takes 0.25 seconds. We have to calculate a number of things, which are: number 1, efficiency of the engine, average power of the engine; number 3, energy that is extracted as heat from high temperature reservoir for every cycle, means QH; and then number 4, the energy that is delivered as heat to low temperature reservoir for every cycle, means we have to calculate QL in this part number 4. And in the fifth one, entropy of the working substance change as a result of the energy transfer from high and low temperature reservoirs, means that the change in entropy in QH and QL means in high temperature reservoir and low temperature reservoirs. The given data is summarized here like this: that high temperature reservoir is at 850 kelvins while low temperature reservoir is at 300 kelvins. The work done is given as for one cycle, means in each cycle it performs 1200 joules of work, and the cycle takes 0.25 seconds to complete. Let's go towards the solutions. Number 1, very simple formula to find out efficiency of the engine. You know, epsilon is used to represent efficiency, and it is equal to 1 minus TL over TH. Sometimes you will also see modulus or vertical bars on each side. That is just this is a very simple formula. Efficiency epsilon is equal to 1 minus TL over TH. We know these formulas. We simply insert the values of the TL and TH here, and we perform the calculation, and we get 0.647, which we can round off to 65% approximately. So the efficiency of this engine is around 65%. Now in part 2, we are required to calculate average power of the engine. So we know that power is equal to work done in unit time. So work done, we know that is 1200 joules, and time for each cycle is 0.25 seconds. We put these values here, we calculate, and we get 4800 watts or 4.8 kilowatts here. Both of these parts are very simple. Now the part number 3. In this, we have to calculate the energy that is extracted from high temperature reservoir. In every cycle we assume that it is same. So QH is equal to the work done divided by the efficiency. So we put these values here: 1200 joules divided by 0.647, which was the one we calculated in part number 1 of this example. So we get 1855 joules. So this is the energy which is extracted by the Carnot engine from high temperature reservoir. The modular sign indicates that this is a magnitude, and Part number 4, the energy that is delivered as heat to low temperature reservoir. We know that the work done is actually equal to the heat energy absorbed minus the heat energy rejected to low temperature reservoir. We can write them like this: the magnitude of, or the modulus of, high energy absorbed from high temperature reservoir minus the energy rejected to or transferred to low temperature reservoir. The difference is equal to the work done. As you might remember that the Carnot engine absorbs some heat QH from high temperature reservoir, convert a part of it into work, and releases rest of the energy to the low temperature reservoir. So from there we have this formula: the work done is equal to the difference between the energies absorbed and rejected, the energy absorbed from high temperature reservoir and the energy rejected to the low temperature reservoir. We simply put these values here now. So after rearranging, we solve for QL, or the energy which is rejected to low temperature reservoir, or the energy that was delivered to low temperature reservoir in every cycle. So QH is the energy absorbed from the high temperature reservoir. We have calculated it here, this one, and the work done is 1200 joules. The difference is equal to 650 joules. Means that the engine absorbs this amount of energy from high temperature reservoir, performs this much work, and sends rest of the energy to low temperature reservoir. Okay, now on the last part, the fifth one, change in entropy. The change in entropy for positive transfer is given by this thing, this formula. You know that the change in entropy is equal to the heat energy transfer divided by the temperature at which that heat energy transfer takes place. So in this case it will be TH, the temperature of high temperature reservoir, okay, and QH is the heat energy which is absorbed from high temperature reservoir. We insert values, perform calculation, and we get 2.18 joules per Kelvin change in the entropy of the high temperature reservoir. Now the change in entropy of the low temperature reservoir. The negative energy transfer means that the energy which is released from the system to the surrounding. Here the surrounding is actually the low temperature reservoir, that is why we are calling it negative transfer. Positive transfer means that the energy is transferred from the surrounding or some source to the system, because high temperature reservoir gives energy to the system and low temperature reservoir absorbs energy from the system. That's why it is called as positive, and this one is called as negative energy transfer. So during this transfer, delta SL is equal to QL divided by TL. We know the values, simply put these values and perform calculations, and we get this answer. Why it is negative? Because this much energy is being released from the system, or this much energy is being reduced from the system and going out to the low temperature reservoir. That is why we have put this negative sign with this energy transfer. So as you notice that the magnitude of both is the same. The energy transfer, the positive energy transfer, means from the source, from the high temperature reservoir to the system. It has increased the system, it has increased the entropy by 2.18 joules per Kelvin, and when the heat is rejected to low temperature reservoir, it has reduced the entropy by 2.18 joules per Kelvin. So the net change in the entropy will be equal to 0 for one cycle of the Carnot engine, or during one Carnot cycle. That's all. I hope you learned. This was a very short tutorial, only one example with about the Carnot cycle. If you have any questions, you can discuss with me, and I will share some more examples with you.